Hi, welcome back. In today's video, we're going to talk about how to find the domain of function operations. Now, in our previous video, we spoke about how to evaluate functions, right? How do you add two functions together? How do you subtract them together? How do you multiply them? And how do you divide them? Well, today we're going to go deeper. We're going to look at the domain of each of those new functions. If I add them, subtract them, multiply, or divide them, can I find the new function and identify the domain of the new function? Now, for domain, it would help to be familiar with the different domain of the general functions. For example, the domain of a quadratic. Are we familiar with the domain of a linear function? A cubic function, a square root function. There's a lot of different functions we're going to be talking about, right? And our goal is to be comfortable and familiar with how to read or identify the domain of those kinds of functions. So let's get to it. In a previous video, we spoke about how do you find and evaluate at a location. For example, how do I go about finding the sum of these two functions at 2? So what we did is we took the function of x at 2, the function of g at 2, and we found the sum. We went to 2 as the input. F is going to give you 3. When g is 2, the output is 6. And then the outcome is 9. Now, would I be able to do that for, let's say, f plus g at 0? If I went to 0, notice how f doesn't exist over here. The only function that exists up here is g. So I can't really find the value of f at 0 because it's not because 0 is not part of the domain of this function. This function, f, only exists between 2 all the way to 10. And g exists from 0 all the way to 6. So in order for us to be able to combine these two functions, whether that's addition, subtraction, multiplication, or division, in order to combine them, I have to use values where both functions exist in. And that's in this range. I can go to 2 and I can find that the output is 3 and the output is 6. I can add those two, I can multiply them, I can subtract them, I can divide them. I can go to really anywhere inside this box because this is where the two functions coexist, where they overlap. So in order for me to add two functions together, I need to first identify what domain do both equations exist in simultaneously. And one way to do that is you can find the domain of the original function, f of x. The domain goes from 2 all the way to 10. So I can say from 2 to 10. What is the domain of the g of x function? Well, g exists from 0 all the way to 6. So in order to find the sum of these two functions, the domain can only exist where these two overlap. And that's between 2 and 6. For any values in here, whether it's this one, whether it's here, or anywhere in the middle, I can even use all the other decimals, right? I can add them, I can subtract them, I can multiply them, and I can divide them. So the domain is going to be the same for these next three. I can't divide numbers out of this box because g exists, but f does not. I cannot multiply them or subtract them over here because f exists, but g does not. So the domain is actually going to be the same for all of these. And we can use this as f minus g of x. We can use an equality notation from 2 to 6. Or we can even switch over to the interval notation, where we use the brackets, right? From 2 to 6. Same thing for division. You can use any of the notations that you prefer, as long as you're explaining that the function can only exist between these two x values. Okay, so today I'm going to show you how to do this with general functions. Here's a general scenario with the these two graphs. We're going to now use functions like cubic functions and square root functions and quadratics and things like that. And I'm going to show you two methods. Okay, we definitely want to pay attention to finding the domain when we're dividing. And I'll explain a few examples here in a little bit, because these will always be the same. Whatever domain we find for addition, subtraction, and multiplication will always be the same. But the domain here sometimes varies. And we'll do a few examples to talk about why that happens. So here's our first example. I want to find the domain when I add these two, subtract these two, multiply them, and divide them. To do that, I need to know what the domain is for the original functions. So I'm going to switch back and forth between a graphing calculator so that you can see this, right? Ideally, we know what a quadratic function looks like, and we know the domain from a quadratic or a linear function, but we can always rely on our calculator to help us with that. So let's graph these two functions. Let's graph x squared plus 2x plus 4. When I graph that function, I can see that the domain, the x values, goes from negative infinity to positive infinity. So the domain here goes from negative infinity to positive infinity. What about the linear function? If I were to graph negative 3x plus 6, now notice how this one goes from negative infinity to positive infinity as well. So it has the same domain. Are there any values that exist in f that are not existent in g? And since both of them go from negative infinity to infinity, I can add any value together on f to any value in g, because they both overlap in every aspect. So the domain here is from negative infinity to infinity. If I were to subtract them, same thing. I would go from negative infinity to infinity. And when I were to multiply them, I can go from negative infinity to infinity. The only time I have to be careful is when I'm dividing. And let me explain why. If I were to divide these two functions, x squared plus 2x plus 4, divided by negative 3x plus 6. If I were to divide these two, I'd have to be careful when I have 0 as a denominator. I can divide any number by any number except 0. When I divide by 0, I get an undefined number, meaning the value does not exist. So my goal when I'm finding this right here, when I'm dividing two functions, is I'm always going to set the denominator equal to 0. And I'm going to solve for x. So I'm going to set the bottom, whatever the bottom is, negative 3x plus 6, set it equal to 0, and let's solve for x. I'm going to move the 6 to the other side. I'm going to divide both by negative 3, and I get x equals positive 2. So now, when I graph this function, the division one, I'm going to pay close attention to x equals 2. Give some personality. Okay, so for all of these functions, the domain will be from negative infinity to infinity. But what happens when I divide them? Let's take a look. If I divide the two functions, look what happens. We said something happens at 2. So let's just graph what happens at 2. What if x equals 2? Let's change the color here so we can see a little bit better. When x equals 2, does it ever reach that value? No. This imaginary axis that I just drew in, I can take it off. That axis is an imaginary value that will not ever exist. The function will go to negative infinity, all the way to the left, all the way to the right, except at 2. So the value does not actually exist at 2. There's nowhere on the graph where there's an output at 2. We call this a vertical asymptote. And you might remember this word from Algebra 2, right? A vertical asymptote is an imaginary axis or line on the graph where the value does not exist in the function. Because if I plug in 2 into my equation, 3 times negative 2, I get negative 6. And negative 6 plus 6 gives me 0, which is something that does not exist, right? I cannot divide a number by 0. So what's going to be my domain? Well, I'm going to go back to the graph. It's going to go from negative infinity all the way to 2. It's going to skip 2, and then it's going to go from 2 to positive infinity. So we're going to modify our domain from negative infinity to 2, and then from 2 to positive infinity. There is a gap here at 2. Notice how I do not put the bracket because 2 does not actually exist in the value. It's going to be everything from negative infinity up to 2, not including 2. It's not part of the function. And then it's going to pick up again from 2 to positive infinity. So whenever we divide functions, things can get a bit funky. Okay? These 3 will be always the same. It's the f divided by g. That something different will occur. So here's our first method. I can go to the graph. Like, how would I describe this first method? Here, let's describe these methods. When I'm adding, subtracting, and multiplying the functions, my first method would be, let's do this into steps. Step 1. Identify the domain of each individual function. So find the domain of f of x and find the domain of g of x. Then you want to figure out graphically for what x values. Determine what x values both functions share in common. Right? Since they both in our previous example went from negative infinity to infinity, all values existed on the first function and all values exist in the second function. So where do they overlap? What do they share in common? Negative infinity to infinity. And that'll always be true when you're adding, subtracting, and multiplying. Identify where they exist, and wherever they overlap, whatever they share in common, the intersection of both domains will give you the new domain of any of these 3 scenarios. Now, for division, we broke this into 2 steps, right? Step 1, set the denominator equal to 0 and solve for x. Once you find that x value, sometimes 1, sometimes 2, depending on how many values you get for your solution, you're going to want to look at that part of the graph. So step 2, look at the f divided by g graph and pay close attention. This is C. Pay close attention to the number that you found in the previous step. Okay? So for these three, we're going to have two methods. For division, we're always going to have one approach. Let's talk about the second method. My second method, I'll do this in a different color, maybe it helps. My second method, I'm actually going to add the functions and subtract the functions and multiply them and divide them. I don't really care about the individual domain for each function. I only care about the result of the sum. I actually want to create a new equation and add these two together. So I'm going to take the first function, x squared plus 2x plus 4, and I'm going to add the second function to it. Right? This represents f of x. This represents g of x. When I add the two functions, I actually get a brand new function. And I spent time in my previous video talking more about how to do this for all the scenarios. Okay? When I add them, I'm going to get x squared. These two are like terms. I get negative x. And then these two at the end are like terms. 4 plus 6, I get 10. So now instead of finding the domain of each function and identifying the overlap, I'm just going to combine the two functions into one. And then from that new equation, identify the domain. So let's do that. Let's graph the new function. Instead of graphing these two equations, I'm only going to graph the result of the sum of the two. And that's this one. Notice how when I combine the original functions through addition, what's the domain? Well, it goes from negative infinity to positive infinity. The domain does not change. Same as above, right? It's just a different approach. Either way, what we're describing here is where do these two functions coexist? And you can do them individually. Where do they overlap? Or you can combine them into one new equation and then find the domain of the new equation. And that'll work for subtraction, multiplication. It'll work for any of these three methods. I can actually subtract the two equations, graph it, and identify the domain. So that would be my method number 2. And your goal here is to decide, right? What method works for me? What approach works for me? What do I prefer? So method number 2, step 1. Combine the two functions by performing the given operation. So you can add the functions, you can subtract them, you can multiply them. You're going to create a new equation when you add them together or subtract them together or multiply them together. Then you're going to graph the new equation and describe the domain. Division, again, will be the same for either. You will only have one method for division. It's multiplication, addition, subtraction that you get to decide. Are you more visual? Do you want to look at all the graphs and then describe the domains? Where do they overlap? Or do you want to combine them, create one equation, and just look at one graph? So let's give one more example from here. Let's just try one more. If you feel confident after this example, you can pause the video now. If you would like to see another one, keep playing. I'll do one more example to show you another scenario that kind of summarizes all of this into one case. So here I have two functions. I want to know where do these two exist. So I'm going to graph them. I'm going to graph the first function, x minus 5. Right? X minus 5 looks like this, from negative infinity to positive infinity. That's the domain. What about the second function, the square root of x function? If I graph that one, it only exists on the right side, the positive numbers, starting at 0. Because I can actually take the square root of 0, so 0 will exist. But notice how for this square root function, the negatives do not exist. So the domain for this function is from 0 to infinity, where 0 is included. So where do these two, for what x values do they both share in common? Where do they both coexist? I can look at the graph. They both exist on the right side of the graph, on the positive values. So what's the domain if I add the two, subtract them, multiply them, right? What's going to be the domain? The domain will be from 0 to infinity, meaning the right side of that graph, right? The positive numbers, including 0. 0 can be plugged in here, and I get a number, and 0 can be plugged in here, and also get a number. And I can add them, subtract them, and such. So these will all be from 0 to infinity. Again, we're looking for the domain of where they both coexist, and that's the right side of the graph. Now, what happens when we divide them? Remember, division has its own rules, right? We're going to divide the function x minus 5 divided by the square root of x. I want to know, step 1, when does the denominator equal to 0? Set denominator equal to 0. It'll always be the denominator. Because remember, we cannot divide by 0. This gives me an undefined value. The number does not exist. Like the functions break at 0. So let's find out where that is. Set the denominator equal to 0 and solve for x. If I want to leave x alone, how do I get rid of the square root? I do the inverse. I square both sides. That allows me to cancel the square root and just leaves me x equals 0 squared, which is 0. So when I go to the graph, I'm going to maybe pay close attention, right? Pay close attention to what happens at 0. I got to graph this though. I need to know what it looks like to define my domain. So let's graph it. When I graph the two functions being divided, look what happens here. It creates a curve, right? This function is a straight line. Then we have a square root, which is a slight curve. And when I divide them, I get this curve. Now, what's the domain here? We said, pay close attention to 0. What happens at 0? Well, notice how at 0, if I create a new equation, x equals 0, let's make this a dotted line. Notice how at 0, the line never really touches it. It's a vertical asymptote. So what's my new domain? Well, the new domain will be everything from 0 to positive infinity, except that at 0, it'll never actually exist. It does not exist at that point. Decimals and your calculators are very helpful here to identify what's really happening at certain locations. So the domain changes a little bit. This one will be from 0 to infinity as well, but we're going to use the parentheses because 0 does not exist in this graph, while it does in the other ones. Alright guys, I hope this has helped. Don't forget to like and subscribe, and as always, we'll calculate later.